I was just about to ask myself if my beautiful partner remembered to put my lunch in a box, and then I remembered that my beautiful partner is the Dutch Mary Poppins, so of course she freaking remembered to put it in a box, you idiot. ID, phone, wallet. Let's get this done. Good morning, Pittsburgh. Good morning, Pitt Undergrad Neuro peoples. Getting another late start today. But it's beautiful today again. Mid-September weather is still killing it. Watch out, here comes Chris. Whoa, holy man. A lot of squirrel dropped pine cones there. So I'm going to try and get in most of the introductory stuff before we get down to the bottom of the hill as usual. Good morning, everybody. Today we're covering what I think is an extraordinarily difficult set of papers. Again, it seems like the primary idea is to introduce you to some of the faculty at Pitt, and I think in that sense, this course is going to present a nice level of survey for you, and it's going to challenge you a lot. I mean, you're going to have to work if it keeps up like this, because this is just a beautiful example of where modern biology is at. And this paper is a great test of how up to speed you may or may not be on. Check that out, speedometer. Because in order to understand this paper, you're going to need to know enough about biology, at least if you want to understand it completely, their hypothesis and their motivation. Hey, horsey. Lekker. He's rolling. In order to understand their motivation and their hypotheses and all the things that they're trying to accomplish in their lab, as represented by these two papers, you're really going to have a pretty good idea of what this disease does, and this disease is pretty complicated. And what's beautiful about it is they actually understand quite a bit about it, how the disease apparently works. And a lot of their information, this is all background information, a lot of the background on this disease is indirect evidence, but the indirect evidence is pretty strong. I mean, maybe I can cover that later, but I don't think that in this ride we need to worry about that. I mean, it's got to be more about finding the scientific process in this lab and how they apply the scientific method to this question. And this question is really cool because essentially you have an autoimmune disease that affects neurotransmission in a very specific and special way. And so to understand this disease, I think the best way to go about it would be to first make sure that everybody's on the same page as far as how neurotransmission works. And so how how does the nervous system work? How do signals transfer from one brain cell or one nerve cell, in some cases from a brain cell to a nerve cell? Let's call them all neurons. How do neurons talk to one another? And then to realize that the neuromuscular junction, where neurons talk to muscles, is just a very, very specialized synapse, a very, very specialized connection. And, you know, this is, again, sort of sidebar information, but the neuromuscular junction is designed to be very reliable and very scalable, obviously, so that you can get all the ranges of muscular contraction that you're used to using every day. And if you're an athlete or a dancer, then you know that, you know, there are so many intermediate muscles and muscle groups and subtle ways that muscles interact. And this is all produced by precise nerve signals and precise execution at the neuromuscular junction. But the neuromuscular junction isn't that different from any other connection between neurons. And that's because at the neuromuscular junction, a neuron is talking to a muscle, and so a neuron here is going to talk in the same way that it would, basically the same mechanisms that it would if it was talking to another neuron. And the first thing we can, again, maybe this is a subject for another video, maybe I'm making a list here right now. We won't talk about how neurons fire action potentials. Let's just assume that everybody who wants to know that has either learned it once or twice and has a book where it's described in cartoon form. But suffice it to say that with the movement of very few cations, very few sodium ions, very few potassium ions in and out of the cell, rather large voltage changes measured across the membrane can be created. Those voltage changes can travel very fast from one part of the neuron to another, and those voltage changes can initiate other channel function. And for those of you who are not, you know, neurobiologists already, one thing to understand about the brain is that there are let's say the vertebrate brain has developed a whole palette of ion channels that it uses to create voltage signals that form the basis of neuronal communication in the nervous system. So these voltage changes, when they reach the end of an axon, they reach the end of a communicating wire between two neurons. These voltage changes reach calcium channels, and the calcium channels let calcium in as opposed to potassium or sodium or chloride. And the selectivity of ion channels is also something that if you're a broad audience member, then that's going to be another sort of concept that is not fit for this discussion, but suffice it to say that if you're not real confident you understand the basics of ion channels and membrane voltage and this kind of stuff, there's a lot of fun reading ahead, because we know a lot about the biophysics of how neurons generate their voltage signals and how they employ them to control ion function. Now, calcium channels are unique because they're very selective for one particular cation, calcium. And calcium is, unlike sodium and potassium, calcium sits at the top of the hierarchy of cations that the brain and cells in general in mammalian systems. This is the cation that they control with the most severity. This is the one that because of its unique role as a cofactor in so many enzymatic reactions, calcium has evolved to be a necessary regulatory point in so many biological, molecular biological cascades that calcium control is paramount to cell survival and cell function in all systems in the mammalian body, but especially or as much in the brain. And so neurons control calcium to the extent to which you can barely measure it free calcium inside of a neuron at any given moment. And spikes in free calcium are essentially signals of relevance for plasticity, for changing the strength of connections, for gene transcription, and for protein production. And so that follows then that wherever you put channels which are selective for calcium, wherever you put calcium channels, things happen. And so at the end of an axon between two neurons which are connected, or at the neuromuscular junction where motor neurons are driving skeletal muscle activity, there is release of neurotransmitter which is driven primarily by a change in calcium in the presynaptic or at the end of the wire. And that change in calcium is driven primarily by P and Q type calcium channels, and the relevance of P and Q type, oh no, here we go. The relevance of P and Q type channels at this time is just like an X and Y type thing. Suffice it to say that these guys are important for letting the calcium in and allowing vesicles to bind and release their neurotransmitter into the synaptic cleft, or in this case the neuromuscular junction. So this process is timed, the calcium is released through these channels and very quickly taken up by buffers and other controls, so that the calcium signal goes very quickly through a peak and then back down to near zero. So you can release on a temporal basis and also on a sort of amplitude basis as much as you need to release. And synapses in the brain can of course have different short-term dynamics, and we can talk about that later. But let's just keep it simple right now, and that is that the voltage changes in a neuron pulse down the axon and pulse through the dendrites. And anywhere where this voltage change occurs, if there are calcium channels which can open or are open, then those calcium channels will let in calcium, and in those immediate regions of the neuron there is potential for things to change. And so it's the timing of these calcium signals and the relative amplitude, the presence of these calcium channels and their function, that allows this system to work so harmoniously. And this disease that's in this paper is an autoimmune disease that appears to, hypothetically, in their hypotheses of the disease, not this lab's, but the general field, the hypothesis is that there is antibodies made which affect the function of PQ-type PQ-type calcium channels in the neuromuscular junction that leads to a severely debilitating loss of skeletal muscle control. So of course that's a bummer, but it's also a disease that seems to present an enticing road to understanding, in that it's not every disease that has a very specific mechanism. And autoimmune disease actually oftentimes do have a very specific mechanism, because they are defined by it. And can you find it, you know? And in this case, they have been able to nail it down. So what we have to also gloss over, and we may come back to in the afternoon after I've read both papers better, well, thoroughly, whatever. Sorry, I was out of breath there for a minute for some reason. I guess the smoke or something. The air looks good today, but it doesn't smell very good. As a biologist, then you're going to have to use your model of how the immune system works and see antibodies somehow attaching to the functional pore of P and Q type potassium channel, or P and Q type calcium channels, and interfering with the way they gate or interfering with the way that they conduct calcium, and thereby changing that what should be a very high fidelity temporal and spatial release of neurotransmitter across a muscle group turns out to be a kind of a fizzing out of turns out to be like a fizzing out of a signal, and results in extreme muscular symptoms. I'm kind of fumbling over that because I don't know what to say when I'm choking on exhaust, but I think the thing to try and get in your head here is what the moving parts of the clock are, or the moving parts of the mechanism are, and that is that you've got calcium channels, and they're letting calcium in, and very, very much responsible for the proper function of the neuromuscular junction. And so voltage signals are coming down the axon of the neurons, and when they reach the end of that axon, they get to a place rich in calcium channels, and so that voltage change, which is propagated from the brain down to the muscle via the spinal cord. Whoa, the hell was that? The voltage change results in calcium coming into the end of the axon, and that causes release of neurotransmitter and muscle contraction. In this autoimmune disease, then you have, presumably, the hypothesis is that the antibodies are present in patients for P and Q type calcium channels, keep saying it wrong, are partially or totally responsible for the dysfunction of the neuromuscular junction in these patients. And I'm sure when you read the papers, it will become a little more complicated than that. There will be some subtleties. I think there's one subtlety wherein a significantly sizable group of the patients with this condition seem to have developed it after lung disease. But that's lung cancer, but that's also understandable because in the sense of, I would guess, I don't know, but I would guess there's some good role for P and Q type calcium channels in the lungs, and so then the possibility of an immuno reaction that causes antibodies to P and Q type calcium channels to be manufactured would then result in the same symptoms as all the other times when this happens. I think there just might be one easy way to do it, some connection with the lungs. I don't know if that's true or not, but I think that's what I read, and then it just kind of makes sense that that's the way it would be. That guy was planning on running the red light until he saw me come down. And that's what you got here. It's just a free-for-all. So you got to make sure you get out there and get in front. Always stay in front. If you gotta, just block them. If you get run over from behind, chances are pretty good the bike will go under the car, and then at least you'll be protected from being run over. Except for when the person cuts the corner like this. See that? What an idiot. What an idiot. That's what you gotta watch out for. He's got a handicap thing in his car, but he drives like he's a maniac. I just can't wait for them. It's annoying. I'm gonna get doored on Liberty someday, but they drive so dangerous. That's how I roll. Forget these fools. Holy shit. What is that all about? Damn it. See that? She went to the right, now she wants to go left again. Ah, darn it, I thought I had that. But Joe Whitebeard put the pedal to the metal. Okay, calcium. Neuromuscular junction. Antibodies hit the calcium channels, change the way that they let calcium in, alter their function in some way. Even target them for elimination and endocytosis. That could also be the case, in which case there'll just be less calcium channels there. Could be a paper somewhere showing that already, I don't know. I'm just thinking out loud now. But that's how it's affected. These guys are looking for a way to alleviate these symptoms, and one of the ways that they're thinking about doing it is with a calcium channel agonist, and thereby boosting the calcium signal that occurs. And then if you could boost the calcium signal pharmacologically, you could overcome the immune system's downregulation of the calcium signal. There was some other treatment that had some effect, but not much. And so finding a calcium channel specific agonist for the neuromuscular junction would be very handy for this disease. Sorry for that, my throat is so dry today, it's crazy. Phone zombies are prevalent everywhere. Test. Okay, so welcome back. We're on our way home. And we're talking about P and Q type potassium, there I did it again. We're talking about P and Q type calcium channels in the brain and in the peripheral nervous system. And P and Q type potassium channels are involved in neurotransmitter release in the periphery and in the central nervous system. And they tend to be characterized as high voltage calcium channels rather than low voltage ones like, say, T-type channels. Interestingly, also, they come from the same gene. P and Q type channels are just alternate splices of the calcium, voltage calcium channel 2.1 gene. And so I was saying earlier in the first part of this ride, that first half of the ride, that control of calcium is fundamental to function of neurons, and that where you put calcium channels determines where calcium is released and where calcium shows up. And when calcium shows up, things change. Plasticity occurs, genes are expressed, channels are inserted and removed. Why are you doing that, you idiot? So calcium channels are extremely important in this case, and in this model, calcium channels at the neuromuscular junction are somehow targeted by an autoimmune response, which either removes channels from the membrane and from the end plate, or removes them or blocks their activity. That much wasn't clear to me from my reading. It could have been in the review, which I didn't read that thoroughly. So I apologize for that. I'm concentrating on the experimental paper today on the way home, and the review, I assume, gives you more background information on the sort of actual phenotype that occurs in the disease. So figure 1 in the experimental paper, there's only 4 figures in the experimental paper, and it's pretty straightforward. The idea is that they have this one drug which can do a little bit, but it's very dose dependent. It has a lot of side effects, and so they can get some amelioration of the effects of the disease, but not really anything clinically significant. Not enough to really significantly improve the lives of these patients. So they had found this other drug that was doing something with ATP, and ATP uptake or ATP release within the cell. And they noticed that this drug also had some calcium channel agonist activity. Antagonist is a blocker, like antagonizing your wife. And agonize is, an agonist is something that stimulates, and I'm not sure what agony and agonist have to do with each other, but anyway, an agonist is something that can activate or enhance the function of a particular kind of channel. It could change the kinetics, it could just open the channel. And in generally speaking, they do something to the way the channel functions as a protein, but they don't. An agonist doesn't necessarily need to be an activator. It can also just change the way the channel behaves when it's in the open state or the closed state, and that's what seems to happen with this drug, that it affects the way the channel behaves in the open state. So in the first figure, they just show you that this drug is not really likely to cause cell death at concentrations that it would be used therapeutically. And they just do a simple cell culture assay here, but it's pretty typical in terms of drugs and drug effects to do a culture assay where you just have cultured neurons or cultured cells, and you just look at survival rate as in relation to dose there, and you see that basically at all the doses that they tested, they more or less are not getting any cell death. So that's handy. Jackass in the bike lane for no reason. So after showing that the drug itself is likely not to be causing any cell death, they go right away to analyzing the effects on calcium currents in the presence or non-presence of the drug. So this is kind of a tricky figure, the second figure, because of the way that they display the data. And so I think you kind of just have to make an assumption, although it isn't immediately graphically clear, because the control trace is buried underneath four experimental traces there. So the control trace is supposed to be 100 millisecond stimulation, and 100 millisecond stimulation that results in a very, 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 very punctuated fast current that decays almost to zero immediately. You're such a dickhead. You didn't even use your turn signal again. You see this shit? What I'm dealing with? People with no turn signal. People in the bike lane. People driving like they own the bike lane. It's not even supposed to be for you. You see, this person here, this is a bike lane, you dipshit. So when you look at that trace, the first trace, the control trace, goes all the way down to the same amplitude, we assume. Otherwise they wouldn't show them overlapping like this, I would hope. And instead what changes in the presence of the drug is the fact that the channels don't close immediately. So instead of being an extremely fast peak that decays almost to zero instantaneously after the channels close, now with the drug present, you see that the trace decays as they increase the length of the pulse. The trace decays, it decays. There's more potassium, or more calcium current. And the more calcium current is caused by the presence of their drug. And without that, again, you see that control trace, there's almost no area invisible above the curve, between the curve and zero, because that pulse is an extremely fast downsweep and an extremely fast upsweep again. Whereas all the other ones, they have an exponential return to zero there. That exponential is that extra time, opening time of all those channels, is what is caused by the drug. So that's kind of cool, because the other treatment that they were using is a treatment which extends the presynaptic action potential. Now, if you remember a little bit from the beginning, from the morning, we were talking about how neurons communicate with one another, and they communicate with one another by rapid changes in voltage, which travel the whole length of the neuron and all the branches of the neuron, and they happen very quickly. These quick voltage deflections can cause neurotransmitter release in the axon. They can cause certain channels to be open during certain events. And the timing of these voltage signals are essentially how the brain coordinates its activity. So when this voltage signal reaches the end of the neuron at the neuromuscular junction, there is a depolarization that causes the influx of the calcium. And the influx of the calcium is what causes the release of the neurotransmitter and the subsequent contraction of the muscle. So without that calcium release, you don't get contraction of the muscle. And the previous drug that they were using, this DAP drug, would extend the length of the depolarization associated with the presynaptic action potential, which would effectively provide a driving force for calcium which lasted longer. See this person driving here? Look, she's worried that she's going to hit that other car, but she's got 5 feet on this side of her car because she's not very good at driving. And because she's not very good at driving, she thinks her car is much bigger and requires much more clearance than it actually does. And if there was any kind of driver in Pennsylvania that I despise, it's the driver who doesn't understand how big their tiny car is. Your car is a Jeep. It doesn't need clearance on the right because it's like a station wagon. It's long and yucky, but it ain't very wide. But she's driving in the middle of the road because, you know, that's the way I drive. And it's so annoying because she pushes people out of the way in this scenario. And now look at these idiots, right? They're gonna get around this guy for sure. Oh, you're a moron. Oh my goodness, you're a moron. And now we're gonna see some real genius level driving here. Okay, so anyway, figure 2 then shows that although the amplitude, which is presumably where they overlap on the far left, the amplitude of each of those traces is roughly similar, including that of the control. But when they apply the drug, the decay time of the signal after the stimulation, the decay time is what changes. The decay time is what now gets lengthened and results in essentially a lot more calcium released. That's what's cool about it. So that drug works well at providing a driving force for the calcium, but here's the trick. If in the disease state there are less calcium channels, or in the disease state the calcium channels simply open less, then that driving force can't really do very much. Extending that back-propagating action potential, extending the length of the depolarization at the presynapse won't do anything unless there's holes through which the calcium can flow. And those are the P and Q type channels. So in the disease state, maybe the review told you that there are less channels. Maybe the channels are not packed right together or something like that. Anyway, the disease creates a situation where there's no real effective release. Thank you! No effective release of calcium, and therefore extremely poor muscle control. So figure 1 shows the drug doesn't kill anything. Figure 2 shows a super additive effect. No, sorry. Figure 2 shows, Figure 2 shows that the effect is likely on the open channel. And again, the reason why is because the control trace only differs in that decay. How quickly does the signal, the channel, how quickly do the channels close again? How quickly is the current back to zero? And in the control conditions, current is back to zero extremely fast. But when you add the drug, all that process changes. Look at this jackass. Just cutting me off because he can. Get off your phone and drive your car, please. The lady in the Forester is making a text. So in the fourth figure, what they're going to show, third figure, they show that there's an additive effect. So essentially they get much more calcium if they both use their new drug to help with open times and the old drug to help with a depolarizer, a longer depolarization presynaptically. And so it's easy to imagine why they hypothesized that these two drugs would complement each other. But it's not every day that it works out so pretty. This is a great result. And you see in that figure 3 where they apply the drugs separately and then apply them together, and you essentially restore to control, and that's pretty badass. So now they're going to test the short-term synaptic dynamics of this system, and I think this is one of those things you can really take to the bank. Short-term synaptic dynamics and the way that synapses change during different frequencies of firing or different frequencies of signal is a fundamental aspect of how brain circuits function. And very likely connections with different short-term dynamics function as low and high pass filters. We talked about that in the first General Journal Club, the Henry Markram and Gilad Silverberg paper, where we saw the discovery of different short-term kinetics for different connections between pyramidal cells and interneurons, and between interneurons and other cells. So we know that this specificity is there throughout the brain, And now what they do is they test the sort of short-term synaptic dynamics of this system, knowing that in the disease state the short-term dynamics are pretty poor. And show some typical decay dynamics that they can differentiate from control or from disease. And I think the most important thing to remember here, I won't do that data, you can do that data in the discussion, but the most important thing to start thinking about in your head is the implications for changes in short-term synaptic dynamics. Because if you want to build a really useful model in your head of how neurocircuits work, one of their key aspects is the biophysical properties of the synapses that lie between neurons. And specifically, it's the short-term dynamics of those synapses. It can change the way that information travels from one neuron to another if a neuron sits there, an interneuron sits there waiting for a particular frequency of signal before it will allow the signal to pass, or before the signal will activate it for surround inhibition. And those aspects of neuronal microcircuits have been well documented, but computational neuroscience is still trying to catch up with putting those into the context of functionality. But basically, neurons work together and they sing together to make groups, functional groups, and that functional grouping is some kind of functional clustering, if you will, where the synchronous activity of neurons is able to use inhibitory signals in the cortex to selectively isolate themselves as a functional group by inhibiting those that are not part of the group. And this connectivity is what's going to end up explaining consciousness. It's this kind of connectivity that's going to end up being the basis for most AI systems. And this kind of connectivity is going to be the blame for how the brain works eventually. It's just a question of when we're going to get there. When are we going to be able to bring together our understanding of the physiology with our ability to simulate a network? It's going to be a lot of dangerous driving here, because I left so on time. There's going to be a lot of people trying to pass me at speed because they want to get home. I would say get a bike, but you know, that's being a dick. One. Another one coming soon. go. More rocket style bullshit. Here comes another one. A rocket. He didn't move over. What does he need to move over for? Go! Oh shit. Somebody right on my ass here. So angry, they get so angry. Look at them. They get so angry. And they all don't move over. It's okay. As long as they don't kill me. But man, I can't believe it's 86 degrees out here. Look at this butthead. On her phone, driving in my butthole. Those are the kinds of people I'd like to pull into their driveway and put a face to my palm. But you can't. You can't, because all those people are under the same stress that the rest of us are. They're all unhappy. They're all unhappy because rich people get away with murder in America. Because corporations get away with murder in America. And the only one who pays a price for everything he or she does is the common man. A black woman casts a provisional ballot that didn't even get counted. She gets 5 years in prison. A woman pays $15,000 to rig her SAT for her daughter. Mail fraud, among other things. She gets 15 days and a fine only twice that of the bribe she paid. I mean, seriously, there's no other conclusion to come to than America's a joke right now. And it is. It's a joke because Republicans are allowed to lie, and Democrats are allowed to lie, and people are allowed to have an opinion about facts. And this leads to extreme unhappiness, extreme loneliness. If there's no chance of having a reasonable conversation with your neighbor because they don't believe what you believe, but they're talking about the real world and not about God, that's a real problem. And that's what America is right now. And we got to change that. Young people like you have to change that. You have to be able to ignore the monkey adults that are out there, the old people, and you need to take this world by the balls and fix it. Because if you don't, you're not going to grow up in the world you hope for. You're going to grow up in a world that hasn't really existed up until now. A neo-Nazi world where rich people don't pay taxes and corporations don't pay taxes and people who dig holes have to pay taxes. People who repair houses have to pay taxes. People who go to work every day for 40 or 50 hours a week, they have to pay taxes. But people who inherit their money, they don't have to pay taxes. People that don't build anything every day, that contribute nothing, they don't leave anything behind, they're just shuffling money around in a room, Those people don't pay taxes. And that's what's wrong with the world. That's it in a nutshell. And we need to change that. One journal club at a time, one registered voter at a time. You 18 and 19-year-olds and 20-year-olds, you need to vote. You need to vote. You need to vote. You need to freaking vote. The end.